All right, let's get started here. So, as I had said, this week we're going to be reviewing our last review topic, these electron pushing arrows, so we can draw mechanisms correctly in this course. The latter half of this week will be dedicated to learning these new experimental techniques that you'll be using in the lab portion of the course, IR spectroscopy and NMR spectroscopy. Okay. All right, so electron pushing arrows. Like, as you guys know from last semester, a big focus of organic chemistry is studying chemical reactions. All right, and when we're talking about chemical reactions, we're talking about making and breaking these chemical bonds. And in organic chemistry, we're specifically focused on a particular type of bond because we're always talking about nonmetals. So we're talking about making and breaking covalent bonds. All right, and our covalent bonds are made up of what? So two nonmetals will form a covalent bond, but that bond itself we say is a shared what? Pair of electrons, right? And so that's the most important thing to think about here, is when we're talking about covalent bonds, making and breaking them, we're talking about something that's made of electrons. So in this chemical reaction, what we're really doing is shuffling around those electrons. All right, so for certain reactions, all you really learn is like your reactants and your products, right? What combines with what to make what product. But for some reactions, there's this extra special piece of information that we learn, what's called the reaction mechanism. All right, you actually first talked about reaction mechanisms all the way back in Chem 1B when you were talking about kinetics. It was that extra special piece of information that if you knew, you could figure out what the kinetics of the reaction are. All right, so importantly, that's what our reaction mechanism tells us, is the step-by-step details of that bond making and breaking. At the molecular level. All right, so yes, bonds are being made, other bonds are being formed, but in what order, right? Like, what exactly is happening? If we were to jump into our magic school bus and shrink on down and watch this chemical reaction, what would be the series of events that would have to occur in order to lead us from reactant to product? Okay? And in organic chemistry, when we're talking about our reaction mechanism, we're going to show the movement of those electrons. All right, those are the keys to that bond making and breaking, since bonds are made up of electrons, using what are called electron pushing arrows. Okay. For some reactions, all we'll learn is, what reactants make what products. For some reactions, we don't even know what the mechanism is, but other reactions are well studied, and we do know the exact details of how that reaction occurs. And so we'll learn this extra special piece of information, the mechanism, and it'll help us sort of better understand those reactions. All right, so first, let's look at kind of a simple reaction here. We're going to look at a chemical equation first. So this will be a simple acid-base reaction, one of the first ones you would have learned way back when in general chemistry in Chem 1A. We mix hydroxide and hydrochloric acid together. What two products do we get? Water and our chloride ion. All right, so this would be our chemical equation, our reactants and our products. But now we're going to look at the reaction mechanism. All right, and so in order to do that, we got to look not just at our chemical formulas, but our Lewis structures or our chemical structures. So we have our hydroxide. We know by our bonding patterns that that oxygen has that negative charge living on it. All right. We got our product, water. And we know from our bonding patterns, chlorine likes to have three lone pairs and one bond, meaning it has a formal charge of 0. If it has a formal charge of -1, like in the chloride ion, that means all of its octet is made up of lone pairs, right? So you got 4 lone pairs on that chloride ion. Okay, and so in order to do our mechanism here, what we want to do is take a step back and play the spot the difference game here. All right, what bonds are being broken in this reaction, and what new bonds are being formed? All right, so everybody take a step back, look at this equation here, and figure out what's being broken and what's being formed in our reaction. Because our mechanism should show the movement of those electrons. Is being broken. Boom. And what new bond are we making? Hydrogen and oxygen. All right, so we got one bond being broken and a new bond being formed in this chemical reaction. And as we said, these bonds are made of what? Electrons. And electrons are particles. They can't be created or destroyed. Right? So that pair of electrons in this bond that's broken, it went somewhere, right? It's got to be accounted for on the left-hand side of my reaction equation here. Likewise, this bonding pair over here that was formed, where did that pair of electrons come from, right? All my electrons are accounted for down on the board here. So importantly, what we can do is now play the spot the difference game, but specifically focusing on lone pairs. We'll see that our number of lone pairs have changed from the left-hand side to the right-hand side as well. If we look, our oxygen on the left has 3 lone pairs, but only 2 on the right. That's because this lone pair went into creating my new oxygen-hydrogen bond, right? It was that lone pair that became that bonding pair of electrons. It didn't just come out of thin air. It was originally a lone pair, and then it became a bonding pair. Still that same pair of electrons. Likewise, this bond, my hydrogen-chlorine bond, where did that pair of electrons go when that bond got broken? On the chloride, right? If we look, my chlorine on the left has 3 lone pairs, but it's got 4 on the right. Where did that extra lone pair came from? Well, it used to be a bonding pair of electrons. Okay? And so that's what our mechanism is going to help us do, is show this new bond that got formed and this old bond that got broken. All right? My mechanism here, my electron pushing arrows, I'd have one that started at that lone pair on the oxygen and reached out to grab that hydrogen. This would be my bond formation arrow. And then I would also have another one showing my bond breaking, so starting at that hydrogen-chlorine bond and then dragging that pair of electrons over to just being on that chloride ion. So here's now my bond breaking arrow. Okay, so these curved arrows here, these are our electron pushing arrows, and they show how our electrons are moving throughout the course of this reaction here. This mechanism is fairly straightforward. It's only one step. Some mechanisms are many more steps. All right, we chose an easy one to start out with here. But importantly, they're showing my lone pair becoming this bonding pair, and this bonding pair becoming this lone pair, right? We have one bond that's being formed and one bond that's being broken, all right? Okay, so we got rules for these electron pushing arrows. Our first rule is really just a reminder that these arrows show the movement of electrons, not atoms. All right, so going back to our simple example here, this first arrow is showing that I'm grabbing this lone pair and dragging it over here to form that new bond with that hydrogen, right? I'm moving that lone pair of electrons, right? Likewise, my second arrow is showing that I'm grabbing this bonding pair of electrons and dragging it over so that it's just living on that chloride ion, right? I'm showing the movement of those electrons in my reaction mechanism. Importantly, since our electrons are negatively charged, we're going to want to make a note that we need to watch out for any changes in formal charges. All right, so those bonding patterns that we discussed last class period are going to be really important to keep in mind. Since we're moving around electrons, we're necessarily changing the formal charge of things in our reaction mechanism. One thing that we can note that's going to help us out, kind of like an easy double check to do when you're all done, is we need to keep in mind that our net charge is going to be conserved from one step to another. All right. So charges are just notoriously easy to lose track of. All right. So having like a little extra double check to help us out is going to be super helpful. What do I mean by my net charge is conserved? Well, if I look at this mechanism here, over here on the left, I have a net charge of -1, right? My hydroxide's negative, this one's neutral, so net, my charge over here is -1. Well, it better also be -1 on the other side as well, right? Because again, that net charge is conserved. So if I look over here, my water's neutral and that chloride ion has a -1 charge. Maybe you forgot your bonding patterns to spy that chloride has that -1 charge, right? So just keeping in mind this net charge being conserved, you start drawing over here. You're like, all right, something needs a negative charge over there. I have to have that conservation of my net charge. All right. Our next rule is that the base of that arrow must be at a pair of electrons. So either a bond or a lone pair, but the base of the arrow is always at a pair of electrons. All right, and again, we can convince ourselves of that by going back to our simple example. In our first arrow, the base of that arrow is at a lone pair. In my second arrow, the base of that arrow is at a bonding pair. But again, the base of the arrow is always at a pair of electrons. All right. And then lastly, the head of that arrow must be at an atom. All right, that atom is accepting that pair of electrons. All right, so let me just kind of clarify a very important point here, because some organic chemistry textbooks kind of differ in their enforcement of this rule. All right, the Wiley textbook is probably my favorite, except it does get this wrong and it drives me nuts. And we're going to make sure to do it the right way here in this course. All right, so if I want to show this pair of electrons coming down here, I cannot have it start at the pair of electrons. That's good, we need that. But I'm not allowed to have it point in the middle here, because electrons don't accept other electrons, right? So this would not be correct. Instead, if I'm going to show that coming down, it needs to end at an atom here. So this would be the right way to show that. Okay, so again, the head of the arrow is always at an atom. The base of the arrow is always at a pair of electrons. Okay, when you're doing your electron pushing arrows, make sure that you're not clicking on bonds, but you're clicking on atoms when drawing those arrows. All right, so we have our rules for drawing our electron pushing arrows. The other thing is we're going to see certain patterns over and over again for these arrows. And sort of identifying which pattern it is that we're looking at, or which pattern it is that we need to draw in, will help us to do our mechanisms correctly. All right, so we have bond formation arrows. Okay, and as we showed in our example mechanism here, a bond formation arrow is one that's going to start at a lone pair and then become a bonding pair. All right, so a bond formation arrow, this means that we have a lone pair becoming a bonding pair. All right, we can also see bond breaking arrows. And again, if we go back to our example and we look at this bond breaking arrow, we can see that it starts at a bonding pair of electrons and turns it into a lone pair of electrons. All right, so bond breaking is when we have a bonding pair becoming a lone pair. All right, so bond formation means we have a lone pair becoming a chemical bond, becoming a bonding pair of electrons, or we can break bonds by turning that bonding pair of electrons into a lone pair. All right, we're going to leave a little bit of room here because we'll complicate things a little bit later, but we're going to start with just these two patterns. Okay, and in our sort of study of these electron pushing arrows, we're first going to worry about following them. So I'm going to put down some arrows, and you tell me what the product of that step of our mechanism is, and then we'll worry about drawing in the arrows ourselves. All right? So you're going to take a few minutes, and we got 3 examples here. You're going to tell me what the next step in the mechanism is by following these electron pushing arrows that I put down. And the first thing you're going to do is identify it as falling into one of those 2 categories. It's either a bond breaking or a bond formation arrow. All right, so figure out which category it belongs in, and then tell me what the product of that step in that mechanism is. All right, let's go do this first one here. Which one of our two patterns are we looking at? Is this a bond breaking or a bond formation arrow? So this would be a bond breaking arrow, which means I'm going to turn this bonding pair of electrons into what? Into a lone pair. All right, so I'm going to draw my carbons. I'm going to have broken that bond, and now my chlorine has 4 lone pairs. All right, this is probably the hardest example of the 3 up here for following your charges. All right, so if we look here, my chloride is got that bonding pattern of that -1 formal charge, right? 4 lone pairs, no bonds. And if I look, what am I missing here? I need a positive charge, right? If I look over here on the left, everything's neutral. That means over here on the right, everything's got to be neutral as well. So if I have a minus charge in there, I better have a plus charge in there as well so that it all evens out to be 0, okay? Where does that plus charge live? On our carbon here, all right? Carbon had a happy complete octet with its 4 bonds, and then it got this pair of electrons taken away from it, right? Leaving it with an incomplete octet or that +1 formal charge. Okay, this is what, a bond breaking or formation arrow? So this will be forming a new one, and particularly between which 2 elements do I have a new covalent bond? Carbon and sulfur, right? So I'm going to form a new carbon-sulfur bond. Because importantly, it's this pair of electrons right here that's going to become that new bond, right? So sometimes people link up these molecules incorrectly, link them up at the carbon or something like that. No, that pair of electrons had to come from somewhere. It was on that sulfide ion. All right, so I got my 4 carbons. Now I'm going to draw my new carbon-sulfur bond. That's that pair of electrons. All right, and it's still got those 2 carbons. And now 2 lone pairs. Am I missing any formal charges on the right? No, everything's cool. It was net charge of 0 over here, so it should be net charge of 0 over here as well. All right, and then this last one here, I got 2 arrows. So let's go one at a time here. This one here would be what? Bond breaking or bond formation? So that one would be our bond breaking arrow, which means that pair of bonding electrons is going to become a lone pair. And this one down here, that would be a bond formation arrow. All right. So since I got a now carbon with 4 bonds, I'm going to draw sort of 90-degree angles just to space everything out. I have my oxygen. It had 2. Now it has that extra lone pair, right? This pair of electrons in that carbon-oxygen pi bond is now going to become that lone pair. All right. Likewise, I have a new carbon-carbon bond. This lone pair on my carbon is now this bonding pair, and I have my triple bonded nitrogen as well from that cyanide ion. Okay. All right, my new carbon-carbon bond here. And then what am I missing? Formal charge. My oxygen's got that bonding pattern for that -1 formal charge. I could also just note that since I had a net charge of -1 over here, I better have a net charge of -1 over here as well. Cool. All right, so we were following these electron pushing arrows, right? I put these arrows in, and you told me what the product of that step would be. Okay, now we're going to do sort of the next game here. We're going to draw in the electron pushing arrows ourselves. Okay, so first of all, this is kind of a preview as to when we start our discussion of alcohols. Alcohols are something that you've kind of encountered a bunch, but we've never specifically focused on in this course. One of the reactions of alcohols that we're going to show is that if you combine a tertiary alcohol with a strong, what are those, halogen acids, you get an alkyl halide and water. All right, so this is my chemical equation. But for this particular reaction, we'll also study the mechanism for that reaction. And this is the first step in that mechanism here. All right, so starting out with our two reactants, we're going to form this intermediate here. All right, and what you're going to do is you're going to put in the electron pushing arrows that would take us from A to B on this one. All right, so for our mechanism, you're going to fill in the missing electron pushing arrows over here on the left. That would lead to our intermediate over here on the right. All right, identify what bonds are being broken, what bonds are being formed, right? And then put in those proper arrows following our patterns. If it's a bond being formed, it should start at a lone pair to become a bonding pair. If it's a bond being broken, it should start at a bonding pair and turn into a lone pair. All right, so am I breaking any bonds in this first step in our mechanism? What bond do I need to break? This bond right here we got to break. And do I form any new bonds? My oxygen, hydrogen. All right, so if I'm going to break this bond, I need to put that pair of electrons somewhere. Got to turn it into a lone pair. So where's that lone pair going to be? All right, I'm breaking this bond, which means I'm putting that pair of electrons where? At my next step, on that chloride ion. All right, likewise, if I'm forming a new bond here, I have to have started at a lone pair. Where does that lone pair live? On our oxygen. All right, so I'll have a bond formation from that lone pair to that hydrogen. It's my new oxygen-hydrogen bond. And then I'm going to have a bond breaking, starting at that bonding pair and moving it over to that chloride ion. Okay, so the first step in my mechanism here is to protonate that alcohol oxygen. All right, I'm going to get rid of my coloring scheme here so we don't get confused for the next step. Okay, again, I'm going to give you, actually we'll do both at once here. So I'll give you the rest of our mechanism here. We need to fill in the electron pushing arrows on step B that would lead to our intermediates in step 3, step C. And then finally we need to fill in missing electron pushing arrows over here to lead us to our overall product for our reaction. All right, so complete this mechanism here by filling in those missing electron pushing arrows. so to get from here to here, am I making any new bonds? I don't have any new bonds. I'm breaking this old bond right here. All right, so I need to turn that into a lone pair. Where's that lone pair going to be? On my oxygen, so let's break this bond. Okay, and then down here to finish this off, I need to do a bond formation. I need to create this new bond. Where did that pair of electrons come from? That chloride ion. All right, so I'm going to drag that lone pair down here to my carbocation to create that new bond. All right, so these together are our reaction mechanism for this reaction of our alcohol. All right, we're going to do one more here. Okay, again, you're going to fill in the electron pushing arrows needed first to create our intermediate, and then put in the electron pushing arrows at our intermediate that leads to our product. All right, so for the sake of time, let's work on this together here. I need to break this bond here, which means I need to turn that bonding pair into a lone pair. And we can see our oxygen now has this extra lone pair. So I'm going to move that pi bond pair of electrons up onto that oxygen. I also need to create a new bond between carbon and oxygen. So that's going to have originated at a lone pair. In this case, that lone pair lives on that hydroxide oxygen. So in order to get my intermediate here, I have this bond formation and bond breaking arrows. All right, moving over to our intermediate. How do I get from our intermediate to our product? Well, I need to create a new bond, reform that carbon-oxygen pi bond, all right? Which means I got to start my arrow at a lone pair. Where did that lone pair live? On my negatively charged oxygen. And I need to break this carbon-chlorine bond right there. Where's that pair of electrons going to go? Onto that chloride ion, all right? So I'm going to break this bond here, putting that pair of electrons on my chloride. And for this bond that I'm going to form, remember we have to start at a lone pair and end at an atom. So I got to point it all the way down there to that carbon atom that's accepting that pair of electrons. All right, and so that will be our mechanism, turning this acyl halide here into a carboxylic acid. Those are one of the reactions we'll study later in the semester. Cool. All right, we left some room under our patterns for electron pushing arrows. There's one more that we could see. And this is when we have bond breaking and formation all in one shot. All right, so a bonding pair of electrons will become a new bonding pair of electrons. All right, so one single arrow to accomplish this both, right? Breaking a bond and forming a new one with just one arrow. All right, this we see when we have pi bonds. Okay, not every time we have pi bonds, as we just showed in the previous example, but when we do have pi bonds either forming or breaking, we could see it be one of these breaking and formation patterns here. Okay, so an example would be starting with the first functional group that you kind of were introduced to, alkenes. All right, if we react these two together, our mechanism looks like this. Okay, so this one down here is just a normal old bond breaking arrow. Putting that pair of electrons from that hydrogen-chlorine bond onto a chloride ion. All right, but this other arrow here starts at a bonding pair, and it will become a bonding pair as well. So this is now our new bond breaking and formation. All right, to be clear, it's breaking that carbon-carbon pi bond, and it's forming a new carbon-hydrogen bond. All right, so if I do my product here, I'm going to explicitly draw my new carbon-hydrogen bond to show that this pair of electrons that was that carbon-carbon pi bond is now this carbon-hydrogen bond over here. All right, but what am I missing from my intermediate? The charge. Okay, so again, we got that net charge business. I have a neutral net charge over here on the left. Everything's got to be neutral over here on the right. So since my chloride ion has a -1 charge, there's going to be a positive charge in there somewhere. Okay, let's see if we can't figure out where that positive charge should go. So if we think about our implied hydrogens over here on the left, I have these each have an implied hydrogen. So let's put them in over here on the right. We can see that one of those carbons, specifically the one that held on to that purple pair of electrons, right? It used to be a carbon-carbon bond. Now it's a carbon-hydrogen bond on that same carbon. That one's happy. It's got a complete octet. The other one, though, got that purple pair of electrons taken away from it, right? Leaving it with an incomplete octet, or that positive formal charge. Okay, let me see if I can't kind of illustrate this here. All right, we had this carbon-carbon pi bond here. If we look at what happens to that carbon over there on the left, when this pair of electrons swings around to form this new bond with hydrogen, that carbon over there on the left got that pair of electrons taken away from it, right? So it's left with an incomplete octet. The bottom line is one of your carbons will have that new bond because it held on to that pair of electrons. The other one is left with an incomplete octet or that positive formal charge. Okay, again, carbocations, very difficult to spy, so that's when our whole paying attention to our net charge being conserved is really important. Okay, cool. Last thing we're going to do is we're going to add to our notes here for our patterns one that we will never see. All right, and that is a lone pair jumping to another atom. All right, in all of our bonding patterns here, we will never see a lone pair just becoming a new lone pair on a different atom. Right, so if our electron pushing arrow is starting at a lone pair, that means it must be forming a new bond. Lone pairs don't just jump from one atom to another. All right, you can kind of convince yourself there'd be no way to do it without breaking somebody's octet. All right, so we're just going to put this down because this is a common mistake people make, that this is one pattern that we will never see here, a lone pair jumping from one atom to another. Again, if your electron pushing arrow is starting at a lone pair, that means it must be becoming a bonding pair. Cool. All right. That does it for our review from first semester material. And next class we'll discuss IR spectroscopy, one of these lab techniques you'll be using.